Alright, welcome everyone to another lecture. So in this lecture we're going to review the DFS or Graph Traversal In-Depth First Search Algorithm. So what is depth first search? Depth first search algorithm is some algorithm which helps you to traverse a graph. Traverse means explore the graph, okay? Visit all the nodes of the graph. So the principle of this algorithm is pretty straightforward. It basically starts with a first vertex, any random vertex for a graph, or if it's tree, then we're going to have to start with the root node of the tree. So we start with a vertex, and then we visit it, and then we're going to visit all of its neighbors, and then from their neighbors we're going to visit their neighbors, and then from their neighbors, and then we're going to visit all of their neighbors, and so on and so forth. This happens recursively, okay? So we start visiting all of the neighbors, we keep visiting as far as we can get before returning, okay? So that's the idea of depth first search. So let's say, for example, we're going to traverse this graph, and let's say we're going to start with node 0. So the first thing that we're going to have to do is to mark this node as visited, okay, so that we don't have to visit it again, okay, later. So I'm going to color the node in yellow. So coloring it in yellow indicates that the node is already visited. So we visit node 0, and then we're going to try to visit all of its adjacent nodes, all of its neighbors. So it has node 1 and node 2 as neighbors. So we're going to try to visit them. But first we have to make sure that they are not visited yet. Okay, because if they're visited, then we don't have to visit them anymore. So node 1 here is not visited, so we're going to visit it. Now we are inside node 1, we are inside vertex 1. So from vertex 1 we're going to do the same thing. Okay, we're going to try to visit all of its adjacent nodes that we did not visit before. The first adjacent node is 0, but 0 was visited before, so we're not gonna visit it. Okay? We're not going to visit 0. But we're going to try to visit 4, since 4 is our second neighbor that was not visited before. So we're going to try to visit 4 through this edge here. So 4 is now visited. Okay? The same thing here. 4 is going to try to visit all of its adjacent nodes. So 1 is its first adjacent node, 2 is its second adjacent node. So we're going to visit 1, and then we're going to visit 2. But 1 is already visited, so we're not going to do anything about it. We're just going to visit node 2. Cool. And note here, it doesn't matter which node to start with as long as they are both adjacent. So for example, 2 here, let's say the example of 5 here. 5 here has a neighbor 4, it has neighbor 8, and it has neighbor 7. So it doesn't matter if we either start with 4 or with 8 or with 7, because we're going to visit them all in the end. So it doesn't matter which one to start with. So back on track. Now we are inside node 2. So from node 2 we're going to try to visit all of the adjacent nodes. So we're going to visit node 0, but then when we reach there we find out that it's already visited, so we're not going to do anything about it. Okay, we're going to try the next neighbor, which is 4. 4 is visited, so we're not going to do anything. 3 is not visited, so we're going to visit it. Okay, cool. So now 3 is visited. The same thing here. 3 is going to try to visit all of its adjacent nodes. It has adjacent node 2 and it has adjacent node 6. Adjacent node 2 is already visited, so we're not going to do anything. but adjacent node 6 was not visited, so we're going to try to visit it. So let's try, we're trying until we hit there. So it's not visited, so we're going to make it visited and continue execution from there. Now we are inside node 6. Now node 6 has two adjacent nodes. It has adjacent node 3 and adjacent node 4. Adjacent node 3, so we're going to try to visit it, but as soon as we get there we find that it is already visited, so we're not going to enter there, okay? We're not going to visit it again. And then we're going to try to visit vertex 4, and then we find out that vertex 4 is already visited, so we're not going to enter there. We're not going to visit it anymore, okay? So we're just going to return. So we don't have any other adjacent node from 6 to visit, so we're going to return again. So now we are here, so we're going to return to 6, and then we're going to return to 3. And then from 3, we don't have any other vertex to visit from the 3, so we're going to return back to 2. And from 2, we don't have any other vertex to visit, so we're going to return to 4, from where we came from. And then from 4, we have visited the first node, the first adjacent node, which is 1, and then the second adjacent node, which is 2, and then basically our third adjacent node is this node 5 here. So we have 5. So we're going to visit 5. And it's not visited yet, so we're going to visit that 5 there. And then from the 5, we're going to visit its adjacent node. So its first adjacent node is 4. But 4 is already marked, it's already visited, so we're not going to enter there. And then the second adjacent node is 7, so we're going to try to visit 7. It's empty, it's not colored, it's not visited, so we're going to mark it as visited. And now from 7, we're going to try to visit its adjacent nodes. It does only have one adjacent node, which is already visited, so we're not going to do anything. So we're going to return back. So we're going to return back to 5. And then from 5, we're going to continue execution. We're going to visit the next unvisited adjacent node of 5, which is 8. So we're going to visit 8. And then 8 is not visited, so we're going to mark it as visited. Again, from 8, we're going to try to visit all of the adjacent nodes that were not visited before. We have only one adjacent node to 8, which is 5, but it's already visited, so we're going just to return, okay? We're not going to do anything inside 8. So we're going to return to 5, and then from 5, we're going to continue execution. Visit all the unvisited adjacent nodes. We don't have any because we've visited them all, so we're going to return back to 4. Now 4 has visited 1, it has visited 2, it has visited 5, now it has to visit 6, but 6 is already visited, so it's not going to visit it again. So the only thing remaining for 4 is to return. It doesn't have anything else to do, so it's going to return to 1. 1 has visited all of its adjacent nodes, so it doesn't have anything else to do, so it's going to return again. Now 0 has visited 1, now it has to visit its next adjacent node, which is 2. But it's going to find out that 2 is already visited, so it's not going to visit it again, so it's going to return to the main program. In this way, we have visited all of our graph. We have explored all of the nodes that are reachable from vertex 0, the vertex that we've started it with. Okay, so if we print out the nodes that are the order of the nodes in which we've visited our graph, it'll be something like this. It'll be 0, and then we visited 1, and then 4, and then 2, then 3, then 6, then back to 3, back to 2, back to 4, and then to 5, and then to 7, and then to 8. So this is the order in which our program would print the nodes if we were to print them whenever we visit any of them. Now let's say that we have, for example, two other nodes, node 9 and node 10, that are connected together, but they are not connected to node 0. So in this case, node 9 and 10 will not be visited, okay? We're going to return to our main program without being without ever visiting 9 or 10. So in that scenario, if we want to visit all of our graph, then we're going to have to iterate through all the nodes, making every one of them every time our starting node. So we start visiting from 0. 0 will visit all of these yellow nodes, and then we're going to start visiting from 1, but 1 is already yellow, so it's not going to visit anything. 2 is already yellow, 3, 4, 5, 6, up to 8. All of them are already yellow, so we're not going to visit them anymore. But when we reach to 9, 9 is our starting vertex now. So 9 will be visited, and then it'll try to visit its adjacent node, which is 10. So 10 will be visited, which will try to visit its unvisited adjacent node, which it doesn't have any. So it's going to return back to 9. So it's going to return back to 9, and then from 9 is going to return to our main program. And then we move to 10. 10 will be our starting vertex. We try to visit 10, but 10 is already yellow. It's already visited, so we don't have to visit it anymore. Cool, so this is the basic idea of the depth first search. Now let's write a function, a simple function that will translate this theorem into a pseudocode. Okay, so it'll be something like this. It'll be graph DFS, which takes the graph G, and then it takes the starting vertex, let's call that U, and then it takes some visited array. So this visited array will contain whether node number I is visited or not. So it'll be something like this, okay? Visited, that has a bunch of values. These values are of type Boolean. So for example, if 1 is visited, then we're going to say visited of 1 equals true. If node 2 is not visited, then this will contain false. Okay, so depending on the content of the array of that index, of the index of that node, depending on the content whether it's true, then that means that that node is visited. If it's false, then it's not visited, okay? So node 1 here is visited and node 2 is not visited. Cool. So this array is initially all filled with false, meaning that all the nodes are not visited, and whenever we visit a node, we mark it as visited. So here we visited node U, so we're going to mark it as visited. But before doing anything, we're going to make sure that the node was not visited before. So if U was not visited, so if not visited of U, let's change that. If visited of U, if the node is already visited, then we're just going to return, okay? We're not going to do anything. Otherwise, we're going to mark this node as visited. So visited of U will take true. And then we're going to iterate through all of its adjacent nodes, and then we're going to try to visit them. So let's say we have an iterator E, which is of type edge node. So this iterator will basically loop through all the edges that are connected to vertex U. So E takes the neighbors of U, and then we're going to iterate. So E is a node of a linked list, so we're gonna say while E is different to null, then we're going to do some stuff, and then some stuff here, and then we're going to increment E. So E takes its next. And let's use arrows here. So E takes its next. That's and while. So we said that we're going to iterate through all the edges that are connected to node U. So for every edge, we want to recursively visit the node associated with that edge. So we're going to call the same function, that's graph DFS. We give it the graph G, but then instead of visiting the node U, we're going to visit the node V. So that's EV. Okay, that's EV. And of course here we're going to give it the visited, so I don't have room to write there, so we're going to add the visited array. Okay, and then we close the function. So that's graph DFS of G, comma E, arrow V, comma visited. And that should do the job. Okay, that should do the depth first search traversal. For real code implementation, you're gonna find that in the next video.